All right, so we are now segueing somewhat abruptly to observational things. I will be partly summarizing the cluster cosmology measurement field, and to a large extent summarizing the work that has been done by KIPAC's X-ray cosmology group. You can see a lot of these collaborators have done their time here at KIPAC. So, you were all paying close attention Wednesday afternoon. I don't have to tell you again what a cluster of galaxies is, but I should say why we would think to use them to study cosmology. In a nutshell, they're big, so the budget of stuff that they can hang on to gravitationally, the baryonic versus dark matter, should be roughly similar to the universe as a whole. They're young in the sense that their global properties that we can measure are predominantly determined by their formation, so cosmology and gravity, rather than intricate gas physics, which comes into play when things cool down. There are qualifiers on both of this, which I'll get to in a minute or two. And also we have multiple independent observational windows onto these objects, which give us somewhat redundant information, and that means that we can control our systematics fairly well. So I'll be covering two cosmological tests that we use galaxy clusters for, mostly focusing on this first one, gas mass fractions, which give us a probe of the expansion of the universe, and I'll focus on that mainly because these are our most recent results, and so I can show you something new. And the second half will be the more well-known growth of cosmic structure using clusters to trace that growth. Okay, so this gas mass fraction, which we call F-gas, what is it? How does it work? As I said before, clusters are big, so approximately speaking, the content in baryons and dark matter that they have should be similar to what's in the universe as a whole. It also turns out, because they're young, the vast majority of mass in the baryons is in the form of very hot X-ray emitting gas that has never had a chance to cool down in the history of the universe. And so roughly speaking, if I go out, say with an X-ray telescope, and measure the gas mass and the total mass, take the ratio of the two, then I've measured the ratio of baryon density to total matter density in the universe, modulo this nuisance parameter here, of course, which we call the gas depletion parameter. So that the key thing that makes this useful at all is that we think we can put theoretical bounds on this depletion parameter fairly robustly from simulations of cluster formation and growth. And also, that depletion parameter is expected to have very small scatter from cluster to cluster. It's something that we can also verify observationally. Just looking at this expression here, we like to use cluster F-gas data in conjunction with measurements of Big Bang nucleosynthesis and local Hubble expansion measurements. Those things basically nail down omega B, and so the clusters then give us a very nice tight constraint on the total matter content of the universe. There is more to this, and that all hinges on the fact that when we look at data from a telescope, we don't just directly pull off F-gas. If you work through all the various factors of flux and angular size that have to be converted to emissivity and physical size, what we measure is a combination of F-gas and the cosmic distance to the cluster to the power 3/2. So we're going to call that a feature in the following sense. If we have a theoretical bound not just on the depletion parameter itself, but its evolution as a function of redshift, then I can use cluster gas mass measurements as a function of redshift to constrain not just omega matter, but also the distance redshift relation, in other words, the expansion of the universe. So let's see what simulations actually tell us about this depletion. That's a critical part of all this. Here on the left-hand side in this panel, I hope you can see fairly well the results of some hydrodynamic simulations by Planellis and Baryonic, The different colored lines here are depletion parameter profiles, so as a function of radius, the depletion parameter from simulations that have three different implementations of gas physics, ranging from essentially nothing to cooling and star formation to cooling and also heating from AGN feedback. The qualitatively most obvious feature of this is that there's a large disagreement at small radii, and generically it's the case that at the centers of clusters, things are very complicated and we don't really think that we get the right answer. This is the volume of the clusters where the statements that I made earlier about things being relatively simple and the gas being relatively simple, those all start to break down. However, if we forget about the complicated volume of the center of the cluster and look farther out, say in a spherical shell, about this conventional radius, about a quarter of the virial radius, then it turns out that there is actually very, very good agreement between these simulations that have different implementations of gas physics. It isn't particularly obvious from this figure, I'll admit, because these are cumulative profiles, so this disagreement at the center sort of persists as you go out. But if you go into the simulation data, just ask what is the ratio of gas mass to total mass in a spherical shell at this radius, and actually all three of these things line up with one another extremely well, and they also agree extremely well with completely independent simulations by different groups. So we have a certain amount of confidence then that if we only are looking at predictions that exclude the cluster center, we have something which is reasonably robust. As a function of redshift, these are similar predictions. So that upsilon of z function that we need in order to constrain cosmic expansion has this prediction, basically no evolution or very little evolution as a function of redshift. It's something that should hold as long as we're looking at the most massive clusters, which we normally quantify in terms of their temperature. That's a nice observable quantity. So if we look at the most massive clusters in the universe, we expect as a function of redshift and also as a function of mass, there should be a single value of this depletion parameter which applies across the board with relatively small scatter. There's one more thing to be a little bit concerned about, and that is if we're using X-ray measurements of cluster gas to measure the total masses of clusters, then we are forced to make the assumption that the gas is in hydrostatic equilibrium with the dark matter potential. And you might guess that for a typical cluster which is not in hydrostatic equilibrium, that's going to introduce a bias and a significant scatter, which is the case in these other sets of simulations by Nagai et al. However, what you can see here in this corner, the filled in points down here, is that if we restrict ourselves not just to the most massive clusters, but to very massive clusters that are also dynamically relaxed, that bias, although not zero, is at least as small as it can be, and we expect something less than about 10% with relatively small scatter. The critical piece here is that today in 2013, we finally now have the technology to actually directly constrain the amount of residual bias for these massive relaxed systems by comparing the X-ray data directly to weak lensing, gravitational lensing data. Okay, so from those considerations, we have what looks like a relatively simple plan, which we have followed in a series of papers that I swear will be written up any day now. First step is to just go out and identify a sample of the most massive dynamically relaxed clusters in the universe. We will measure the gas mass fraction for those clusters in a spherical shell that excludes the center of the clusters. We will use weak gravitational lensing data to directly constrain the residual bias from the hydrostatic mass assumption. And then with a expectation for the depletion parameter from simulations, we can constrain cosmological models. Okay, so without going into all of the wonderful details of this, we searched through essentially the entire Chandra archive of galaxy cluster observations, some 350 systems or so, looking for appropriately hot, dynamically relaxed clusters. In practice, relaxation was defined in terms of some automated measurements of cluster morphology, which we trained and invented specifically for this purpose. And so of that 350 or so clusters, our final sample has 40 systems, which cover the redshift range from 0 to about 1.1. This is what the F-gas profiles for some of those clusters looks like. Qualitatively, you can see it's small radii, a little bit jargony on the x-axis here, but you can think of this as radii, radius increasing to the right. So at small radii, there's a noticeable amount of intrinsic dispersion between the profiles, but they all start to converge and sort of follow a similar power law at about this spherical shell, which we identified earlier, with relatively small scatter. That holds up if we look at all the clusters together. It's just a little bit harder to see everything when it's jumbled together. So if I plot the data as a function of redshift, you can see where the constraint on cosmic expansion comes from. As I said, to actually derive a physically meaningful F-gas value, you have to plug in a distance. And if I plug in those distances based on a model with no dark energy and quite a lot of dark matter, then there's a clear trend that you can see in the data there, which would be at odds with the expectation of little or no evolution in the depletion factor. On the right, you can see if we plug in something more like a concordance model, the data would look very consistent with a constant. So that should be favored. Of course, the real analysis that we do is much more intricate than just looking at these plots. And we marginalize over various priors on the things that I've described, the gas depletion parameter based on simulations, and the overall calibration of our mass measurements based on a comparison to weak lensing data but I think in the interest of time, I better skip over the details there, unless people have questions later on. So, with this data, we can turn the crank and get constraints on cosmological models. If we look at cosmological constant type models allowing for curvature, these are the constraints that we get from the F-gas data. Omega matter is 0.31 plus or minus 0.04. That's a result which is systematically limited by our constraint on the mass calibration. That calibration, in turn, is simply limited at the moment by the number of these relaxed clusters for which we have gravitational lensing data. So there's a straightforward way to improve that. For omega lambda, we have 0.69 plus or minus 0.2. This is not systematically limited at the moment. It's limited simply by the amount of data that we have. You can see that at higher redshifts, we start to become a bit sparse. So in principle, again, expanding the data set gives us a straightforward way to improve those constraints. This is what the plot looks like if I include as well independent cosmological constraints from other types of data. Of course, the CMB really like us to have a flat universe. The supernova constraints are probably very familiar. Baryonic acoustic oscillations, if you use these same priors on omega b8 squared and the Hubble constant as we do, end up looking something like this. But the main features, of course, is that they all agree with each other more or less very nicely. Everything lines up with this model, 0.3, 0.7 roughly, which we have known and loved for about 10 years now. Okay, of course, the next plot that I show you is going to be for a spatially flat model where dark energy does not have to be a cosmological constant. It does have a constant equation of state, but that can have any other value. And this is what the various cosmological experiments give us for those sorts of models. The F-gas data give us, again, omega matter of 0.3 plus or minus 0.04. That's exactly the same. But for the equation of state, we have essentially minus 1 plus or minus 0.3. And again, that dark energy parameter is statistically limited at the moment, so more data straightforwardly can help us with that. And again, probably no one will be too surprised to see that when we put all these data sets together, we get a omega matter of basically 0.3 and W very much consistent with the cosmological constant value. We can obviously continue combining these data sets. We can look at more complex models of evolving W, and I'll show a little bit of that at the end of the talk. But there is a second half that I want to get to first. And just a parting shot from F-gas, I want to point out the intrinsic scatter that we can measure from these data is actually quite small, 7.5%, which with that power of 3/2 in the distance is reduced down to about 5% in distance. That's why only 40 galaxy clusters can give us constraints that are actually rather interesting like this. So again, getting more data up here should straightforwardly allow us to improve things. The other consequence of that, if there's a very small scatter in the gas mass fraction, is straightforwardly that if we can measure the gas masses for clusters, that gives us a very good proxy for the total mass of clusters, and it is much easier to do. That will be relevant for the second half. So, moving on to the growth of cosmic structure. This is a more complex test, and so there won't even be a single equation in this part of the talk. But broadly speaking, the growth of cosmic structure means going out and counting halos in the universe. So the abundance of halos is a function of mass and is a function of redshift. That's sensitive to a lot of interesting physics out there, primarily the local universe amplitude of the matter power spectrum, but also the total amount of matter in the universe, the amount of mass in the neutrino sector, of course, properties of dark energy, but also properties of gravity, details of inflation, and probably things that I don't know about yet. So schematically, the way it works is this. We have a prediction from simulations of structure formation for the number of things in the universe, number of halos, as a function of redshift and mass, as I said. In terms of observations, we can do a survey of the sky and count how many clusters there are, their abundance, as a function of redshift and not mass, but some other observable, for example, X-ray flux, which you see here. And to get these two things to talk to each other, we need a third ingredient, which we call a scaling relation. That's basically a function that says, at this redshift and mass, the distribution of X-ray luminosities for clusters in the universe follows a particular form. So if we have these three ingredients, prediction, a survey, some additional data, especially mass measurements for clusters, and a good understanding of the selection of the survey and other data so that we can account for observational biases, then we can turn a complicated crank, and again, we can constrain various aspects of cosmology. Okay, so by now there have been a number of successful cluster surveys. The results that I'll focus on here are based on the Ross et al. Sky survey, which is now about 20 years old. I encourage you to not worry too much about all the details that are here on the right-hand side. The main features are that it was an all-sky survey in the X-rays. People went into the data, found clusters, and we are going to be using the brightest, roughly 250 clusters found in that survey going out to redshift of about 0.5. As I said, we need additional data to calibrate scaling relations, predominantly to measure cluster masses. And in the work that I'm showing you, our solution was to basically take advantage of the F-gas style analysis that we had already done. So for those relaxed clusters, we do have total masses measured and gas masses, and as I said, gas mass can be used as a good proxy for total mass. So a subset of those F-gas data are allowing us to constrain that particular proxy relation, which we can then apply to a larger data set. There are some things that I have to note at this point, because I just spent 15 minutes explaining to you that F-gas data by themselves can constrain dark energy. So in this section, we'd like to see what the constraints on dark energy are just from the growth of structure. And in order to do that, I'm restricting the use of F-gas data to just a few very low redshift objects, so we don't get to use this leveraging redshift in the F-gas data, and that means that the constraints on W that you see in a minute really are from the growth of structure and not from these data themselves. The other irritating feature of this particular talk is that the growth of structure results that I'm showing you are from a few years ago. That means they used a previous version of the F-gas analysis, in particular a version that did not have this very nice calibration of the hydrostatic mass bias to weak lensing data. So the mass calibration is different, and just skipping to the end of the explanation, if you would be kind enough to mentally shift all the omega matter constraints that you see in a second over to higher values by about 0.05, that accounts for what we think in a hand-wavy way will be the effect of bringing all the calibration up to date. But we obviously haven't done that quite yet. So again, we marginalize over what we think is a very honest accounting for various systematic uncertainties, which again I won't go into the details of, because it turns out with these data, the only thing that really matters is the systematic uncertainty in the absolute cluster mass calibration. By now I'm sure you've realized that this mass calibration is by far the most important thing for us to address, and that's why the talk immediately after the coffee break will be very focused on that. Okay, so skipping to some results now. This is what we get using the cluster growth data for flat lambda CDM models. The omega matter constraints are going to be very similar to what we get from F-gas data, of course. The interesting new parameter that we get from the abundance of clusters is the amplitude of the power spectrum, sigma 8. The value that we have from these data are 0.82 plus or minus 0.05. But this is a dark energy session, so let me go ahead and allow the equation of state of dark energy to take on other values. So from the growth data now, we have W of about -1 plus or minus 0.2 in agreement with the F-gas data, and of course, in agreement with various other data sets. And like the other cluster experiment, this is a constraint here which is statistically limited at the moment, so an expanded data set will improve things. You can see here the comparison with other cosmological data. This again is a figure which is a few years old, so we have previous versions of CMB data and supernovae and BAO, but qualitatively the picture is very similar. Everything overlaps nicely with one another, and the cosmological constant value of -1 is perfectly acceptable to all these data sets. Okay, I do need to mention that there are people in the audience and people also out there in the wider world who have done very similar studies to the one that I've just showed you. In particular, Eduardo Rosso, who I just saw enter the room a few minutes ago, has done a similar study using optically selected clusters from the SDSS, looking at the abundance of clusters there. Brad Benson has done a similar study using millimeter wavelength selected clusters from the South Pole Telescope. All of these results are encouragingly in very good agreement with one another, which is great. I also feel compelled to mention, even though this is a dark energy session, there's lots of interesting physics that we can get at with cluster growth measurements other than dark energy. For example, comparing with the amplitude of the CMB, we can put limits and constraints on the amount of mass in the neutrino sector, as I mentioned earlier. And we have a potentially interesting and somewhat unique probe of non-Gaussianity in that the cluster signal, that the detailed statistics of cluster masses are sensitive to many moments of non-Gaussianity beyond the first few, the skewness and the kurtosis, which are what people are currently looking for in CMB and galaxy correlation studies. Okay, but returning to dark energy, I wanted to show this now at the very end, constraints from the 2010 growth analysis and the new F-gas analysis on evolving W models. This is the particular model of W that we use here, which basically has a value W naught of the equation of state today, WET at earlier times, evolving somehow smoothly from one to the other. And what you can see here, just qualitatively, is that even in this relatively simple evolving model where we've gone beyond the constant, that very quickly, even using the combination of all the best data that we have now, we wind up with constraints on these equation of state parameters with uncertainties of order unity. So it's true to say that as things stand today, we have lots of very nice data, and it's all very consistent with a cosmological constant model and no spatial curvature and statements like this. But it would be a very different thing to say that we've really dug into any significant extent to these slightly more general model spaces and parameter spaces. So in my last 2 minutes, or probably more like 30 seconds, I will cover my last slide, which is just to mention that in terms of the growth of structure experiment that I mentioned, the next step is going to be incorporating, of course, first of all, the new F-gas analysis that I covered earlier in the talk, and also a larger gravitational lensing data set that you'll hear about a little bit later. That will give us, we think, roughly a factor of 2 improvement in that critical systematic uncertainty to do with mass calibration, and that basically impacts all of the cosmological parameters that I've shown you and should make obsolete more or less the entire talk that I've just showed you. But you'll hear more about that later. And there's a summary slide which basically lists a few of the interesting things that I think clusters have helped us with in the cosmology world and shows my optimism that in at least the next 5 to 10 years, we will be able to do some very interesting things as well. Thank you.
Could you just say quickly what your current upper bounds are on the sum of the neutrino masses?
Okay, sure. So there may be differences of opinion on this, actually. The upper limit that we got in 2010 was the sum of the 3 masses is less than 0.33 eV at 2 sigma confidence. I think some of the more recent work, particularly by SBT and also by Planck, claims to have also a lower limit, although not at particularly high significance. So they have some preference for greater than 0 mass. We basically have our best fit exactly at 0. What was that?
Does that assume flatness?
This figure, yes, does assume flatness. The constraints, if you go to not just curved, but even more general models, obviously blow up a bit, but by less than a factor of 2 or so. I think 0.5 is a number that I remember.
Any more questions?
So how does that change if you assume the Planck CMB results instead of WMAP for this?
For the neutrino specifically?
Yeah.
I have no idea. We haven't done it yet.
But you plan to do it for your next paper.
Oh, yes.
Also a slight change in the Hubble constant, I think.
It'll go down, right? The primordial normalization won't have changed all that much, and the omega matter has gone up both analysis, right? So the late time structure is more. Oh, sorry. I think it should go down, right? Because the primordial amplitude is the same, and there's more matter, there's more structure at the end. The clusters are more massive, right? So there's less room for a drop in the total amount of growth. It's harder to accommodate less growth.
You want higher neutrino mass.
No, so if you had more, right, so if you had a bigger drop in the amount of structure, you would have higher neutrino mass. But it's going to be harder to accommodate a larger amount of growth suppression. Because the new omega matters are higher. The clusters are more massive.
So
We can talk
We'll talk
after.
more, yeah.
I would just add to that, I think the more significant change that we will see comes from the fact that we'll be using a weak lensing mass calibration of clusters. So I don't know exactly how it's going to shift, but on this axis, the cluster constraint is probably going to be the main thing affecting our new result there.